Welcome students. Today we will discuss about partial derivative and directional derivative of a multivariate function. Now I will give you the definition of partial derivative of a multivariate function. Let D be a non-empty subset of R2 and F be a function from D to R. If limit x tends to a, f of x comma b minus f of a comma b by x minus a exists as a finite definite number, then it is called the first order partial derivative of f with respect to x at a comma b, and it is denoted by fx of a comma b or del f del x at a comma b. The equivalent definition of this is fx a comma b is equal to limit h tends to 0 f of a plus h comma b minus f of a comma b whole divided by h. And if the limit x tends to be f of a comma y minus f of a comma b by y minus b exists finitely, or this exists finitely, then we call it the first order partial derivative with respect to y, and we denote it f of y of a comma b or del f del y at a comma b. Here you have to remember one thing. When we are trying to get partial derivative of a certain multivariate function, then this quantity has to be finite. Okay, otherwise we will say the partial derivative at this point doesn't exist. Now I will give the definition of directional derivative of a multivariate function. Directional derivative is nothing but the rate of change of f at a comma b along the vector v bar is equal to limit h tends to 0 f of a comma b plus hb minus f of a comma b whole divided by h. Okay, we call this directional derivative of f at a comma b along the vector v, and we denoted it by this symbol. This limit has to exist finitely. Okay, now I will give you the pictorial view of this definition. Okay, see, here I have drawn the famous xy plane. Suppose your point a comma b is situated at here, and the point v, which is v1 comma v2, is situated at here, and our vector v cap is nothing but a straight line between the point a comma b and the point v1 comma v2. Then the directional derivative of f at the point a comma b along the vector v cap is the rate of change of f at a comma b along the vector v. Okay, now our first problem is show that f of x comma y is equal to xy by x square plus y square when x comma y not equal to 0 comma 0, and 0 when x comma y is equal to 0 comma 0 has partial derivatives at 0, 0, but not the directional derivative in any arbitrary direction. See, at first I have to clear this thing. See, if we put x equal to 0 and y equal to 0 here, then the form is indeterminate form. Okay. But if we are trying to find the partial derivative of this function at 0, 0, then we have to put this point in our domain. Okay, that is why we have to define the function at non-zero point separately and the 0 point separately. And we have to give the value 0 at the point 0, 0. Okay. Now I will do the problem. See how to approach this problem. At first, I will do the partial derivative at 0, 0. See, limit h tends to 0, therefore 0 plus h, 0 minus f of 0, 0 by h, okay, is equal to limit h tends to 0. Now see, f of h, 0 is equal to h into 0 by h square plus 0 square, and this is ultimately 0. Okay, then we put here 0, and as we know, f of 0, 0 is 0, so I put here 0 by h. Okay, but this quantity is independently 0. That is why this quantity is 0. Okay, does the limit exist? And the limiting value is 0, and this is equal to del f del x at the point 0, 0. Okay. Now, limit k tends to 0, f of 0, 0 plus k minus f of 0, 0 by k. Just to give the definition. Okay, is equal to, see here, f of 0, k is again 0. So I am writing 0 instead of f of 0, k. F of 0, 0 is 0. Okay. Similar to this method. This is again 0. So our both partial derivatives exist at 0, 0. Okay. So fx and fy exist at 0, 0. Okay. So we are done. But still we have to show that the directional derivative of this function at arbitrary direction does exist. Okay. So I am erasing the board. limit limit h tends to 0. Okay, f of 0 comma 0 plus h v minus f of a comma sorry 0 comma 0 by, have to change the pen, by h. Okay, where v is equal to the ordered pair b1 b2 and this arbitrary. Okay, now see, though since these points are lying on R2, okay, so the operation between two ordered pair in R2 is this. Okay, and if we multiply a ordered pair by its scalar, then so limit of h tends to 0. See here, f of 0 comma 0 plus h of b1 b2. Okay, by h limit h tends to 0. See, as I defined here, the operation between two ordered pairs, 0 plus h v1, okay, comma 0 plus h v2. H limit h tends to 0, f of h v1 h v2 by 0 minus 0 by h. Okay, now I write this limit h tends to 0. See, what is f of h v1 comma h v2? This is a non-zero point, so we put this point in this expression. H v1 dot h v2 by h square v1 square plus h square v2 square. Okay, and here another h, so I write here 1 by h. Now see that This is the vital step, okay, for us. See, if we tend h to 0, then y by h is tending to infinity. Okay, but as I said in this in the definition of directional derivative, the limit has to exist finitely. Okay, but here the limit exists infinitely. Okay, so we will say the directional derivative at any direction does not exist. Any direction, why any direction? Because v1 comma v2 is arbitrary point in R2. We take arbitrary point. Okay, that is why we can say that the directional derivative of f at 0, 0 along any vector doesn't exist. Okay, so I am just erasing the line, this line, okay, and I am writing this. The limit does not exist finitely. Okay, so directional derivative, okay, finitely for arbitrary points for an arbitrary point v1, v2. So the direction derivative of f at 0, 0 along any direction does not exist. Okay. Now our second problem. Problem 2. Find the directional derivative of f at 0, 0 in the direction of b is equal to what is it? F is equal to xy by x square plus y. Okay. Diagonal equal to 0. Simple. Okay. Okay. So d of v of a at 0, 0 is equal to answer is equal to limit h tends to 0, limit h tends to 0, f of 0, 0 plus h v1 v2 minus f of 0 comma 0 by x. Now limit x tends to 0 in h v1 h v2 minus f of 0 comma 0 by h. Now what is f of h v1 comma h v2? Limit h tends to 0. We put the values in this expression and we get h v1 into h v2 by h square v1 square plus h v2. Okay. Now limit h tends to 0. Okay. That h is it cancel out and see v1 v2 h v1 square v2. Okay, and if we apply the limit h tends to 0, then we get the expression. See v1 v2 by v2. Okay, v2 if v2 not equal to 0, okay, then we can cancel out the v2 and v2. But if v2 is 0, then we cannot cancel out the v2. Okay, so we have to write v1 if v2 not equal to 0. Okay, and if v2 is 0, then we have to assign a value. Okay, 0 if v2 equal to 0. Okay, because the limit exists finitely. Okay, and for non-zero v2, the limit is v1, very finite. But if the v2 is 0, then what we do? We have to assign a value. Okay, and the value is 0. The suitable value is 0. Third problem is if f of xy is equal to x cube by x cube minus y cube minus y cube by x square plus y square when xy not equal to 0. Okay, and 0 if xy equal to 0. Not equal to 0 means at least one of x and y is not 0. Okay, then put that f of x at 0, 0 is equal to 1 and fy at 0, 0 is equal to of x at 0 comma 0. Answer is equal to limit h tends to 0, limit h tends to 0, f of 0 plus h comma 0 minus f of 0 comma 0 by h is equal to limit h tends to 0 c. Now I put h comma 0 in this expression. Okay. H cube minus 0 by h square plus 0 minus 0 by h, limit h tends to 0, limit h tends to 0 c. Here only h. Okay, h by h, and this is 1. Okay, so I put the value of fx of 0 comma 0 is equal to 1. Proved. Now f of fy of 0 0. See, limit k tends to 0, f of 0 comma 0 plus k minus f of 0 comma 0 by k, limit k tends to 0, 0 minus k cube by 0 plus k square by 0 by k, and this comes out to minus k by k. Okay, and this will be minus 1. So we have proved if y at 0 0 is equal to minus 1. Proved. Okay. Now our fourth problem is, let f of x y is equal to x to the power 3 by 2 into e to the power y. Determine fx at 1 comma 2. That means we have determined the partial derivative of f with respect to x at the point 1 comma 2. Okay. Answer. Here is the domain of the function is total R2. Okay. So here f of x at 1 comma 2 is equal to limit h tends to 0, f of 1 plus h, okay, minus f of this by h. Now the limit h tends to 0. What is f of 1 plus h comma 2? That is 1 plus h to the power 3 by 2 e to the power 2 minus 1 to the power 3 by 2, 1 to the power 3 by 2 e to the power 2 h. Okay. Now, okay, maybe I'm replacing this. I have to assume something. Now, assume 1 plus h is equal to z. Okay, so if so, as h tends to 0, z tends to 1. So here we change the limit. Z tends to 1, and here we put z instead of 1 plus h. Z to the power 3 by 2 is square by. Now what is h? H means z minus 1. Okay. So z minus 1. Now limit z tends to 1 is square z to the power 3 by 2 minus 1 by z by minus 1. Okay. Now see, if we apply the limit to this expression, okay, then the upper portion of this function is 0 tending to 0, and the lower portion of the function will also 0. That means it is 0 by 0 form, 0 by 0 form, and it is an indeterminate form. And you all know the L'Hospital rule. Okay. L'Hospital rule. Okay. If you don't know the L'Hospital rule, then go to Google and search it. Okay. What is L'Hospital rule? To apply L'Hospital rule, we have to differentiate the numerator and the denominator, okay, with respect to the variable z. So if we differentiate the numerator, then 3 by 2 into z to the power 3 by 2 minus 1. Okay, and if we differentiate the denominator, then this is only minus 1. And now if we apply the limit, then this gives a definite value, okay, a finite value. So we are applying the limit, and our value is square 3 by 2 1 to the power, what is 3 by 2 minus 1? That is 1 by 2 by minus 1, right? So it is minus e square 3 by 2. Okay, so this is the answer. Here we have to write, we are applying L'Hospital. Okay, so done. Now I am giving you the definition of higher order partial derivatives. Let us consider a function f from D to R where D is a non-empty subset of R2, and let the first order partial derivative of f with respect to x and y be exist and function of x, y. So they may also possess the partial derivatives. Okay, and the partial derivatives of this and this are called second order partial derivative of f. Let us consider a point a comma b from the domain. Then we have this four definition of partial derivatives. Okay, this is f xx, this is f xy, this is f yy, this is f yx. In each of the cases, the limit has to exist finitely. Okay, if any of the limit will not exist finitely, then the corresponding partial derivative will not exist. Okay, our problem 5 is f of xy is equal to xy into x square minus y square by x square plus y square when x comma y is not equal to 0 comma 0, and f of xy is equal to 0 when xy is equal to 0 comma 0, and show that f of xy at 0 comma 0 is not equal to f of yx at 0 comma 0. Okay, then at first I am writing the definition of fxy at 0 comma 0. Fxy at 0 comma 0 is equal to limit h tends to 0, h tends to 0, if y 0 plus h comma 0 minus f of y 0 comma 0 by h. Okay, is equal to limit h tends to 0 f of y okay, but we don't know what is f of fy 0 comma 0 and what is fy h comma 0. We have to find what is f1, we have to find what is fy of h comma 0. Okay, see f of is equal to limit k f of h comma 0 plus k minus f of 0 by okay this equal to limit k tends to 0 f of hk this okay no f limit k tends to 0. I'm putting h and k in this expression and put h and 0 in this expression to get, but we get h into h square minus k square by h square plus k square. And if we make k tends to 0, then is equal to h plus h, then h square is equal to h. Okay. So fy h comma 0 is equal to h. Okay. Then f of y 0 comma 0 is equal to 0. So is equal to limit h tends to 0. What is this? H. H minus 0 by h is equal to 1. Okay. So f of xy at 0 comma 0 is 1. F of yx at 0 comma 0 is equal to limit k tends to 0, limit k tends to 0, fx 0 comma 0 plus a minus f of x 0 comma 0 by k. Okay. Now this okay, but again we don't know the value of x at 0 comma 0 at 0 comma k, so we have to calculate the value. Okay. Now if x 0 comma k is limit, okay, limit, what is the limit? Limit h tends to 0, f of 0 plus h comma k minus f of 0 comma k by h. Okay. And we know this. And what is f of h comma k? F of h comma k is hk into h square k square by h square plus k square minus this will be 0 by h. Okay. By h, and the rest part I am doing here, and this will be limit h tends to 0, limit h tends to 0, okay. And if we apply the limit h tends to 0, then we have k into minus k square by k square. Okay. So we have, so f of x comma this is equal to minus k, and equal to and this equal to 0. Okay. So I am erasing the whole thing, not whole thing, few lines. Now limit k tends to 0. This is minus k. This is, and this will be minus 1. Okay. So f of yx is minus 1. And here in the problem we have to show this. Okay. And here you can see clearly that these values are not equal. So this will add 1. So from 1 and 2 we have f of xy and 0, 0 not equal to before y is just you have to remember the definitions and the problem will be very easy to you. Okay.